everyone. Today we're going to present our integrated project, which is to design a hydrogen processing plant. We were tasked to design a hydrogen processing plant that produces over 30,000 tons of hydrogen a year, and we were required to implement our knowledge from Reaction Engineering 1 and Separation Process 2 subjects. What is a hydrogen processing plant actually? It's the basic fact is that it actually converts natural gas and steam to produce hydrogen. Okay, so now we have already found out how the basic mechanism of a hydrogen processing plant. So this is a rough diagram of how steam and natural gas gets converted to hydrogen. Next is the parties that mass produce hydrogen. They are the petroleum companies, which are Petronas, such as Petronas and Shell, ExxonMobil also, and chemical companies such as Wipro, Unza, Hobbit and Unilever. And next is the examples of examples of hydrogen processing plant. So that is a brief introduction on hydrogen processing plants.
Here is the schematic diagram of the SMR plant, the steam methane reforming plant, and below is the simplified block diagram of the SMR plant. As you can see in the block diagram, the SMR plant is simplified into three parts: the SMR reactor, the water gas shift, WGS reactor, and hydrogen separator. Methane is compressed into the SMR reactor, while water is pumped to the WGS reactor. Both of these streams are heated by the heat exchanger before entering the system. The conventional SMR process used in industries consists of two main steps. In the first step, endothermic SMR reaction takes place at high temperature around 800 to 1000 degrees C. In the second step, the exothermic water gas shift reaction, WGS reaction, runs at a lower temperature around 200 to 400 degrees C. The WGS reactor is modeled as a double shift reactor that operates first at high temperature, which is around 350 degrees C, and subsequently at lower temperature of 200 degrees C. A high temperature of WGS reactor is often followed by a low temperature reactor to increase the hydrogen content while decreasing the carbon monoxide content to 1% or less. The gas stream containing high amount of hydrogen will enter the hydrogen separator. A membrane separation of hydrogen was used for the hydrogen separator in this SMR plant. The hydrogen separator represents an isothermal metallic membrane that produces an almost pure hydrogen stream, which is more than 99% of purity. The stream that exits the hydrogen separator is called the retentate stream, which contains the gas that remains after the separation of hydrogen in the hydrogen separator. The retentate stream is expanded across a throttling valve before entering the combustion chamber. Lastly, the hydrogen should be cooled down to the temperature of the environment before exiting the SMR plant in order to achieve the maximum hydrogen production. So here are the chemical reactions that occur in the SMR plant. In the SMR reactor, the reaction as the methane reacts with water to produce carbon monoxide and hydrogen, which is the desired product. While in the WGS reactor, there's one main reaction, which is a process of water in the form of steam is mixed with carbon monoxide to obtain hydrogen and carbon dioxide. The WGS reaction have some side reactions that produce the unwanted byproducts such as carbon and methane. As you can see here, there are three side reactions occur in the WGS reactor that produce unwanted products. So the catalyst used for SMR reaction is nickel catalyst supported on alumina. The catalyst is most widely used in SMR process because of its high reactivity, can withstand very high temperature, and exhibits good mechanical strength. While iron-based and copper-based catalysts are typically used in industry for HTS, LTS operation, which is high temperature shift and low temperature shift in the WGS reactor. For high temperature shift operation, the catalyst is typically a combination of ferrous oxide Fe3O4 combined with chromia, which minimize the catalyst sintering. And a typical low temperature shift catalyst is used to remove carbon monoxide, and the catalyst is composed of copper, zinc oxide, and alumina. Copper, the active species, remains active at temperature as low as 200 degrees C. The zinc oxide provides some protection of the copper from sulfur poisoning by reaction with absorbed sulfur compounds while acting partially as a support for the copper. Now, both SMR and WGS reactors used packed bed reactors, PBR reactors, as both reactions require catalysts. And the reactions in the WGS reactor are considered as complex type reactions, as both parallel and series reactions happen in the reactor.
Hello, in this part we will discuss the kinetic data and reactor sizing for the steam methane reforming process. So the first thing is we will be looking at the steam methane reactor part of the process, in which the kinetic data we have extracted from an academic journal, and we have chosen the temperature of 700 degrees Celsius for the reaction, and the catalyst used is nickel alumina. So we are using integral method to find the order of reaction, and based on the three graphs that we have plotted, we can conclude that the reaction order for the SMR reaction is first order. Moving on to the water-gas shift reaction, we also extracted the kinetic data from the same journal paper, and we also use integral method for determining the order of reaction. And based on the chart that we have plotted, the reaction is both either zero or first order. However, we decided to proceed with zero order for this reaction. Now we can move on to the reactor sizing part, and we can employ the algorithm for non-isothermal reactor design to determine the amount of catalyst required and the volume of reactor. And we need to make some assumptions to simplify our calculation, and which some of the assumptions is we assume it's an adiabatic reactor with no work done, and also we assume steady state operation with negligible pressure drop across the reactor. And this is just an example of a method on how to calculate the mass of catalyst and the volume of reactor. And the first step is we use the energy balance equation to determine the relationship between temperature and conversion factor. And then we find the relationship between the reaction rate constant and the temperature. And then we determine the rate of reaction with respect to temperature, in which we need to employ the ideal gas equation to find the total concentration inside the reactor. And then we need to determine the rate of reaction per unit weight of catalyst, because this is a packed bed reactor, and it is related to the rate of reaction by the bulk density of the catalyst. And then we can construct the Levin-Spill plot with all those equations that we have developed. And in this case, we assume the inlet flow rate to be 100 mole per hour of methane. And then this is the Levin-Spill plot that we obtained for this specific case. And then we can determine the weight of catalyst based on the area under the Levin-Spill plot. And we have decided to take until the conversion of 30%, because that is the maximum conversion. And we can also determine the volume of reactor. And this is just an example on the method on how to calculate the volume of reactor and the weight of catalyst.
I will present you about absorption system for hydrogen enrichment unit. So after a few research, we got for pressure swing absorption. It is most suitable process for SMR technology, which is enrich the hydrogen, which is also purify the hydrogen. So the other advantages is simple, other than two. So it also low cost operating, and it is most used, which is major application in absorption industry. For type of adsorbent in the pressure swing absorption, the most suitable and the most used adsorbent is zeolite 30X and also BPL4X10 activated carbon. As you can see, the particle size of zeolite 30X is more bigger than activated carbon. Also, the average pore diameter, zeolite is more bigger than activated carbon. So we conclude that for properties, zeolite 30X is more suitable adsorbent for this process, as we know that higher surface area, it will higher the rate of adsorption. First graph, for hydrogen, every temperature it's achieve high purity with a slightly different value, and the highest purity can achieve is 0.3 mole kg per kg with 23 bar at 308 Kelvin. And for carbon dioxide, for zeolite 30X, it can be removed at highest achieved at 298 hydrogen, and carbon dioxide behavior makes zeolite 30X more suitable for enrich the hydrogen. You can see this one. And also this one. And for activated carbon, the graph for hydrogen, every temperature achieves high purity with slightly different too. The highest purity can achieve is 0.47 mol per kg with actin bar at 308 Kelvin. And for carbon dioxide, it can be removed at highest achieved at 298 Kelvin. And for in terms of characteristic, activated carbon is actually more suitable as it will remove impurities of hydrogen. But for isotherm, zeolite 30X shows an efficient result on purity of hydrogen and also removal of carbon dioxide. Therefore, zeolite 30X is the best adsorbent.
Our group has decided to produce high purity hydrogen by using pressure swing adsorption. The basic concept of this process is that the feed mixture containing hydrogen gas is selectively adsorbed by zeolite 13X at relatively high pressure. The objective of this process is to obtain 99.9% hydrogen. So, let's have a look in detail about how adsorption works in this system. As we can see, the feed entering the adsorption tower is the tower adsorbs the other components except for hydrogen gas, which will then be released. Components left will then be dissolved so that the adsorbent can be reused again. Lowering the column pressure, or also known as depressurization, and flowing a part of the impurity-free hydrogen product gas over the adsorbent at a lower pressure known as purging are two common methods of desorption. Our group has decided to use a 10-column 11-cycle PSA process. This process is known as poly-bed process. The reason behind this model is because multiple adsorption towers are more efficient than a single tower. However, we need to evaluate the specifications based on a single tower. To evaluate the specifications, we have to look at the mass transfer zone and breakthrough first. The mass transfer starts immediately, causing the concentration of adsorbate to decrease along the length of the bed until it approaches close to zero. However, the fresh feed still enters the collar, making the portion of the bed the feed touches to continuously exposed to fluid at the feed concentration. As time consumes, the bed part reaches equilibrium with the feed and therefore no mass transfer occurs. The system continues as usual when the section of bed has not yet achieved equilibrium. Mass transfer zone is when the length over which the concentration changes. The mass transfer zone reaches the end of the bed at time T3. Progressively, some adsorbate leaves with the column effluent, which usually is not so desirable. This is known as breakthrough, and time T3 is referred to as the breakthrough time. Based on the breakthrough curve on the right, there are certain informations obtained. The breakthrough time is 2100 seconds. The total time recorded is 2600 seconds. The height is stated from an article to be 0.87 meter, whereas the unused bed height is 0.19 meter. In order to find the height of tower, we need the new breakthrough time, which is recorded to be 15,000 seconds. Therefore, the new height can be calculated and it is recorded to be 4.96 meter. To carry out the calculations in this process, certain assumptions must be made. Number 1. Ideal gas behavior throughout the column. No mass, heat or velocity changes in the radial direction. External mass and heat transfer resistance expressed with the film model. There is no changes in temperature in each particle. There is always constant porosity along the bed. As engineers, we are supposed to come up with modifications or strategies to reach our objective. So, the strategies in obtaining 99.9% production in hydrogen gas is adsorbent with smaller pore size. A smaller particle size enables a higher mass transfer rate, which means a shorter mass transfer zone because the intraparticle diffusion is shorter. Longer bed length with reasonable breakthrough time and cost. A longer bed contains more adsorbent, which allows longer online time before regeneration is needed. Moreover, bed utilization efficiency increases with bed length because the unused part becomes a smaller portion of the overall bed. However, a very tall tower will cost you some money. Purge and pressure equalizer. The proposed PSA sequence increases the hydrogen recovery by introducing a purge step, which uses a recycle of CO2 rich stream and a pressure equalizing step.